After the simple pendulum, let's look at a physical pendulum. So the difference between these two is how we see the mass. In the simple pendulum, the mass was concentrated at the end. And we considered that the connecting cord has no mass. With the physical pendulum, it's different because the mass is distributed along the whole pendulum. So let's take a look at a physical pendulum. And here we're looking at a baseball bat, and you'll notice a couple of interesting things. Here the pivot point is not at the end, and it doesn't have to be with a physical pendulum. So we would normally, with a simple pendulum, we'd think the pivot point being up at the top there. And the other interesting fact is that the pivot point and the center of gravity are some distance h away from each other. Now why is that? Well, if we put the pivot point on the center of gravity, then it's balanced, and it doesn't matter the orientation of the object, it will always be balanced. So there is no oscillation when the pivot point is at the center of gravity. So there has to be some separation between those two. And you notice that you have the mass times the gravity. You're taking a look at the whole pendulum, and the separation h here. And those factors become very important as we do our analysis. Now, because the mass is distributed, we can't use the last analysis to be able to solve this. Instead, we need to use torque. To solve this. And so our torque in the counterclockwise direction has to equal our torque in the clockwise direction. When we talk about torque, we're going to be talking about moments of inertia, I, and we're going to be talking about alpha, function of t, that's our rotational acceleration, and that's going to be equal to negative mass times gravity times h, that gets us our torque. But remember also that that h is the distance that the pivot point and the center of gravity are apart based on the angle is sine of theta t, function of t. And we can rewrite this to get it into a familiar form. Well, we have this sine function in here, just like we had with the pendulum before. So we're going to have to restrict this in the same way with the same restrictions that we had for the simple pendulum. And now we can rewrite our equation in a standard form. And we can solve this like we would any other differential equation, and we'll find that our omega value will be equal to square root of mass times gravity times height divided by our moment of inertia. And all of the other equations for the pendulum that we had before, the standard equation, theta function of t is equal to some theta max times cosine omega t plus phi. And since everything's standard, we know that the frequency is going to be 1 over 2 pi square root mass times gravity times height over moment of inertia, and the period is just going to be the reciprocal, which is 2 pi square root moment of inertia divided by mass times gravity times distance. So that's our physical pendulum. Very similar. The analysis comes out with something very similar to the simple pendulum. The only difference is we have to use the moment of inertia because the mass is distributed along the whole pendulum.